So today's session is on TensorFlow. It's on giving an overview of how TensorFlow can be used to build applications for artificial intelligence. But before we dive into that, even though I've already been given a very nice introduction, I'll still repeat myself pretty quick. So I'm currently working as a machine learning engineer at Buffer. I am also a tech blogger on Medium, and I'm a Google developer expert in machine learning. So before we dive into TensorFlow, I'd like to take a step back and start from really the beginning of how artificial intelligence basically started to change our lives. So going back to 1943, that's when the first mathematical model of biological neuron was built. And this is how a neuron looks like, right? So you have dendrites, you have a soma, axon, synapse. The neuron basically receives information through the dendrites, it processes that information, and then it passes on the output or that processed information to other neurons that it is connected to. And this is what basically inspired the neurons that we currently use in neural networks in machine learning. And right after 1943, when the mathematical models were all being built and were in place. In 1950, Alan Turing basically wrote the first ever paper to question, can machines think? And in that paper, he introduced a test called the Turing test, which said that a person should not be able to distinguish between a computer and another person that it's talking to. So the Turing test, looking at the diagram, suggested that if there's person C and person C is talking to someone behind a wall, right, and person C has no idea, should have no idea that whether it's talking to another computer or it's talking to another human being. So as to say that the computer should be performing so well in conversations or whatever basically it is doing, it should be so intelligently performing that task that the person should not be able to distinguish between a computer and a human. The person should not be able to basically say, no, I know that's a computer, etc. And following that, in 1958, the first ever modern neural network was built, right, using the building blocks of neuron in neural networks, right? The first ever neural network algorithm was built in 1958. And we've all heard the famous name Geoffrey Hinton, the person that we call as the godfather of machine learning. So he started to work on this idea of computers can think as well as humans. And he worked on this idea for 30 years, irrespective of what other scientists thought. And his struggle actually bore fruit in 2012. And since 2012, the advancement in AI has been exponentially sped up, right? So you just saw that Dialogflow can be used to very easily build chatbot, right? That was a very nice session though. But how far chatbots date back is actually very interesting. The first ever chatbot was built in 1966 by MIT. It was called Eliza. It had no voice like an audio, but you could chat with it through a terminal. And this is, so the idea of having chatbots, having this conversational AI, having computers talk to you like humans do, that idea has been in development since 1966, right? And it's only just recently that we have been able to have systems like Dialogflow, IBM Watson, etc. in place to build these things pretty quickly. And then in 2016, AlphaGo goes where no machine has gone before. The computer performed really well in AlphaGo. In 2017, the Stanford algorithm was built to diagnose different diseases using X-rays. And although it performed well on diagnosing all of the different 14 diseases using X-rays. It performed exceptionally well in diagnosing pneumonia, so well that it performed better than the radiologists themselves. In 2018, we had the first self-driving cars hit the roads. And just recently, we had OpenAI bots defeat the championship team in Dota. And in 2018, Google Assistant basically passed the Turing test that I mentioned a while ago. So it performed so well in its conversational AI that a person talking to the Google Assistant could not differentiate whether it is talking to another human or it's talking to actually a computer program. So even in Pakistan, we have a lot of companies who are working in AI and have started to adapt it and use it in building applications for artificial intelligence. And so I'll share two of these examples to show the scope of artificial intelligence, not just around the globe, but also in Pakistan itself. So the first one is language independent segmentation of different areas based on vision. So if you want to, so the goal is to extract important information, text information, and images from PDFs, right? So manually you would basically read that PDF, and someone would read that PDF and highlight the important information, etc. Or you'd have some rule-based things in place. And another way of doing it is through AI, where you can first split it up into logical sections using visions, and then you can extract important information using natural language processing from each of those segmented pieces of segmented logical sections, right? So if a person manually does all of this, it'll take about like roughly 7 to 8 minutes for a 10-page PDF. But for a system built, for an AI system that's built for this purpose, would probably take 30 to 40 seconds for that same PDF. So it's a single PDF versus 15 PDFs through artificial intelligence, right? Another example is installing solar panels on rooftops, right? So normally you have a team of people who come to your house. They look at, they analyze your rooftop. They look at the trees that are surrounding your house. They look at the sun direction, etc. And then they basically figure out the best place for the installation of solar panels, right? If you do this through an AI system, you'd ideally basically take the images and try to split or segment the rooftop into logical areas. You'd identify trees around the house. You'd use the location of the house to understand the sun directions at different times. And you'd use your AI system would, as a result, basically the output would be to give you the best or the most optimal place that the system believes is best for the solar panel installations, right? So if you want to do this for one house, you would have a team of people going to that house doing it. It roughly takes about, like, the whole process takes about like 2 weeks to and then you have a team of people coming in, right? So you have labor, you have time cost. But if you're doing this through the AI system, you can probably process a lot of those house images through the system in a day, a lot of those house images, right? So if I want to have solar panels installed for houses in an entire zip code, it kind of seems very impossible for a team of people going to each of those houses in that entire zip code area and finding out the optimal locations for the solar panels, right? It would take a lots of time, right? Given that you just have one team of people going in or two teams of people going in. So you have labor and you have time cost. And so AI becomes extraordinary, and it appears extraordinary for the reason that it seems to solve problems that otherwise seem impossible, right? And AI appears extraordinary because it achieves speed that is not humanly possible, right? So it appears, and that's what makes it more appear more intelligent, because it is so fast in its system that it would process, for example, 2,880 PDF documents per day, but a human in comparison would not be able to do those many PDFs, right? And the same for solar panels. It would be able to process the entire zip code, houses in the entire zip code using just the satellite imagery. But if that has to be done manually, then you'd need a team of people going to each of those houses in the entire zip code, which kind of seems impossible, right? So AI achieves speed not humanly possible, and tends to solve problems that seem impossible, and that's what makes it to appear extraordinary, right? Now coming to TensorFlow. There are a lot of frameworks in place now which are being used to build AI applications. So you have the amazing PyTorch by Facebook, you have Cafe, you have TensorFlow, and all of these can be built, can be used to build AI applications. But today I'd focus on what TensorFlow basically brings on the table. So TensorFlow is a powerful machine learning framework. It's by Google. It comes with a lot of other tools, and it's expanding. It has a huge community of developers using it, adding more features to it. So the team of TensorFlow and the developers who are using TensorFlow are building things to make it easier for people to build AI applications using TensorFlow. So, for example, introducing TF-GANs library to easily build GANs, and TF Lite for mobile, etc. TensorFlow can be used for both. So uh, it's good for production models, and it's also great for scalability. It's used in both research and in production, and it gives good speed. It is well documented, and the documentation keeps improving. Google itself uses TensorFlow in a lot of its applications, in a lot of its products. So, for example, Gmail uses TensorFlow, Google Photos uses TensorFlow. Even Google RankBrain algorithm uses TensorFlow. So Google RankBrain is the algorithm that when you query something on Google search, so you have an algorithm that runs to give the most relevant links at the top right. So it ranks the relevant links based on which one is most related to your query, right? And that's the RankBrain algorithm, which uses TensorFlow. Now we also have customized and focused hardwares to run TensorFlow models, and that's the Cloud TPU. This is basically a summary of what TensorFlow brings to the table. So you have APIs for data design to design your data pipelines, to pre-process your data, to use data science directly from the TensorFlow libraries. And then you have APIs to build your models. You have TensorBoard to analyze your models. You can save your models. You have TensorFlow Hub, where you have a lot of models that other people have built, and you can use them. You have TensorFlow JS for running TensorFlow in your browser. You have TensorFlow Lite for your mobile applications. And you have TensorFlow Serving for cloud. So starting off with model building. So TensorFlow gives you flexibility in the sense that it can be used by both people who are completely new to machine learning, and they can just use Keras API, where you already have all the layers built in, you already have all the functions in place to train, fit, test the dataset, predict on the datasets, etc., and test the model, train the model. You already have all of those functions in place, and all of those layers, different layers and different that can be used in different models in place, and you can just simply use them to build your model and to test it, predict it, save it, put it in a pipeline, even use it in production. So Keras is greatly used in production as well, and not just for new users and learning. Then you can use the functional API alongside the built-in layers, and you can, and if you want to go into building custom layers, like you want to build your own layer, you want to have your own loss function, you want to have your own matrices, you can do all of that as well using TensorFlow. And this way you have more control over the solution that you're trying to build, right? In case you feel that the other solutions that are already in place do not fit in for your problem. Then you can also use it for research, and you can build literally everything from scratch. So you have functions in TensorFlow the way you have functions in NumPy as well, right? Where you are just to the level of multiplying arrays, etc., right? Multiplying matrices, etc., loading, rotating images, etc. So you have functions to that level as well, and then you have functions which are encapsulated functions where you just have to call a model layer, or you just have to directly call a model. So for example, I want to build an application for cache recognition. So I have the data set that looks something like this on the screen. So I have 10 rupee notes and I have 100 rupee notes, and I collect the data set first, right? And TensorFlow has a image generator API, which you can simply use to, instead of loading each of the images from the dataset, pre-processing them separately, combining them up, stacking them up in arrays, and then processing them so that you can input them to your model. There's something very simple that you can use, image generator in TensorFlow. So all that you have to give to image generator is a directory that a structured directory, right? So in this case, for example, I would have a folder images, and I would have 2 folders inside it, training and testing. And then I'd have further folders inside my training and testing. So the folders inside my training and testing would basically be treated as classes. So my model would treat 10 as one class and 100 as one class, and all the images inside the folder 10 would then be linked to that particular class. So all I'd have to do is basically pass on to my image generator function the path to the training directory. And it would understand automatically that the folders inside are the separate classes and would treat them accordingly. And similarly, when I'm testing it, I would just pass on the testing, and when I'm performing predictions on my testing data, I would just pass on to the image generator the directory for my testing folder, and it would automatically separate out each folder as a separate class. So image generator can also be used. It's a function that you can directly call, and when you're building your models, right? You can call this, you can import image generator, and then you can pass on the directories to it. At the same time, you can also use image generator to do data augmentation on the fly, right? So you can set parameters when you're calling that function. So not just passing the path of the directory, but also setting, for example, the zoom level, the rotation level, the scaling, the rescaling, if there's any, if you want to do rescaling, etc. So you can pass on these and a lot of shear values, zoom value, resize value, etc., etc. You can just set all of these parameters, and when the image generator would load images from these folders, it would side by side also augment those images using the parameters that you have set. And then there's another way. So for cases where, especially in image classification, when there's one good way of starting off with to solving such problems, right? And that is using the data that transformed AI research, which is the ImageNet dataset. So the ImageNet dataset basically has a lot of images, lots and lots of images. So that's 3.2 million images and thousands of classes, right? So you have classes like dog, sailboat, vehicle, craft, etc. You have classes for all the fruits, all the vegetables, or you have classes for all animals, etc., etc. So when, especially with image classification, when we're trying to build simple applications like cache recognition or cache classification into 10 rupee note and 100 rupee note, what would be the best way to do it is to use transfer learning. So the concept of transfer learning is that you transfer knowledge from one model to another, right? So when you have a model that's trained on ImageNet to classify the different classes in ImageNet, it has obviously stored some, it has learned some knowledge, right, by looking at all of those images. So it has a knowledge. So the model has that knowledge, right? So it knows what a dog looks like, what a cat looks like, etc., etc. Obviously, this exact knowledge is not directly transferable. What's transferable is the knowledge that the model has gained about, for example, what's a background and what's a foreground in an image, right? So that's a valuable knowledge to transfer to another model, right? Because for the other model, you're not classifying cats and dogs or trees, you're classifying notes, 100 rupee note and 10 rupee note. So when we use transfer learning, we basically take a model that's pre-trained on another very larger data set, and then we retrain that model for the new data set that we have. So we transfer that initial knowledge that it has learned from the larger data set, and we tweak that knowledge according to the new data set that we're providing it, right? So in that case, it looks something like this, that you have a pre-trained model, you add a few more layers to that model, then you have your images directory, you have image generator that gives images to your model, you perform training, and then you perform evaluation. So there are a few major benefits to this, to transfer learning. The first one is that since you're using a model, a pre-trained model, right? So you're using that the knowledge that it already has from a larger data set. So you need less computational resources when you're training it on the newer data set, right? Because it already has some knowledge and it needs to tweak that knowledge and add basically more new knowledge to that, right? To be able to perform on the custom problem. The second one is, so the training is faster, you use less computational resources, and at the same time, you also can use lesser data, right? So for example, in case of this cache recognition problem, if I had less data, I obviously did not have 3.2 million images or a million images or thousands of images. Maybe I just had like a few hundred images. So even in these cases, this transfer learning concept performs well for problems like these, where you, for your specific custom problem, you have lesser data. So you can then obviously plot the graphs, confusion matrices, accuracy loss graphs, and analyze your model. Now, this is where TensorFlow basically comes into place. So it's an analysis tool that you can import. You can use it in Colab or Jupyter Notebooks, etc. And what TensorFlow, or you can use the TensorFlow dashboard, right? So what TensorFlow does is it gives you graphs for your accuracy, for your loss. It would also displays your model architecture for you. You can also use it to display the images in your dataset instead of displaying them or writing code in your Colabs or notebooks to display images, etc. You can directly use TensorFlow for that. TensorFlow also has recently introduced TF-GANs, which is a library which can be used to build GANs much more easily, right? So you have training data, which are the first two images. As you can say that the first two images are, for example, from the training set. So the model, basically the GANs, generative adversarial networks, would basically learn to associate the different structures in the drawing to how they should be in an image, right? So for example, it learned that something like this is definitely a door, and something like these 3 bars is definitely a window. And then when you would basically pass these images for predictions, so it would create from the knowledge that it has learned, it would create these images all by itself. So these places buildings do not exist. These were created entirely by the network themselves. Similarly, another example of GANs is to a digit generator. And then you can also use TensorFlow to build interesting applications like neural style transfer, which is basically transferring style from one image to another. So you start off with a noisy image and then you take content and style from two different images. So when I say content, content would be the high level features, for example, the Eiffel Tower in an image. And when we say style, style is more like the colors of the image, the edges, the style in the edges of the images, and these are the low level features. And you're basically combining the lower level features from the style image, and these go into the edges, the colors, and the lower level features of the images basically. And you take content from your content image, so the content are basically the higher level features, the objects, etc., and those come as the higher level features in your output image as well. Here's another example. So you can see that using the content image, you're basically retaining the higher level features, for example, the woman here, the door, the mosque, etc. And the style goes into the lower level features, so the style goes into the colors and the edges of the images, etc. So TensorFlow also has TensorFlow Lite. So you can run the machine learning models on mobile and the embedded devices. So it's not just iOS or Android. It's also, for example, Arduino, etc. So the steps to these are simple. You train the model, you use TensorFlow Lite converter to convert your model to TensorFlow Lite, and then you basically run it on the applications that you have built in Android, integrate them basically in your Android app or your iOS app. And in that case, you're not basically, when you're running the model directly on your mobile device, right? You're not you're not putting in that extra computation where you're taking a picture, for example, from your mobile, then sending it to the server where an inference or prediction is performed and the return is result to the mobile, and you see the results, etc. And for this, you whatever Wi-Fi internet connections you'll be needing will be required as well. But when you're using TensorFlow Lite, you can basically do all of that. You can run the model predictions right on your mobile instead of sending them out to a server or to cloud. Here's a simple example of running TensorFlow Lite on Arduino. So you basically have sensory data that you're using to predict gestures, and the model runs on the device when it's predicting. So here the model is running on the device and not on your laptop. You're just seeing the output on the laptop, but it's running right on your device using the sensory data. You can also use TensorFlow to build applications and run them right in your browser. An interesting application of that is POSNet. So POSNet is an algorithm that predicts poses using an image. So in simple terms, these are basically the stick figures that you can see in the images, right? So so the model basically outputs these poses, these stick figures for the images that it's analyzing, predicting on, right? And there was an interesting application built using this, which is called Move Mirror. So Move Mirror is basically, so what they did is they built an entire database of images of different people with predicted poses. So you would so every time you'd move, right? So you have your webcam on and you're moving. So every time you would move, the model would first predict the pose and then match it against something from the database and bring out basically the closest image from the database that your pose is matching against, right? And every time you basically change your movement, you'll be matched again. So the image from the database that you matched against will change. And that would sort of give you this dancing output as you move in front of your webcam. So as you move, your pose would change. You'll be matched against a different image, and the images would change side by side as you move. So this is something, an interesting application that you can try out as well. It's called Move Mirror. And that's really about it on how TensorFlow can be used and has been used to build interesting applications using artificial intelligence. And I am open to questions if there are any. You can also send me questions on LinkedIn. Feel free. Does TensorFlow supports machine learning plus natural language plus? Yes, it does. It supports all three of these. I'm not sure if you're asking or telling me. If you're asking, I am not sure if the dataset is easily available or not.
I think there's no more questions from the QA session.
Thank you for having me. It was a pleasure.
Okay, Aqsa, thank you so much for your talk, and I really hope that all the audience have made something of this. And thank you for sharing all your resources. We have another question before we leave.
Yes, please. Roadmap to learn AI. It really starts with basic programming first. It depends whether, since I have worked more in Python, and I think most people start off with Python programming, and since all the machine learning libraries and everything is easily available for Python language, so it starts with that basic Python programming. Then you should have basic knowledge of what machine learning is, etc. For that, you can take simple courses from Coursera. So you could take Introduction to Machine Learning, or so simple courses to basically understand the different algorithms in machine learning, to understand what deep learning is, what natural language processing is, etc. And when you feel you know those basics well, then you basically jump onto the frameworks, for example, whether it's TensorFlow or PyTorch or any else. Could be either of the two, PyTorch or TensorFlow. They're both great frameworks. So you could start working using those frameworks to basically build applications. You can use datasets from Kaggle, practice on your own, or you can take courses specific to TensorFlow or specific to PyTorch, etc. And side by side, read blogs, read new research papers, and I guess that should go. Some best models to start working with for transfer learning. So models, I think you should, for transfer learning, maybe you should start with image classifications. So you would be able to find pre-trained models on ImageNet very easily. MobileNet, VGG19, these are all, for both of these you can find uh, them pre-trained with ImageNet and then use them basically for classification of images for any data sets from Kaggle, for example, or your own. Thank you.
All right, we have no more questions. Thank you so much, Aksa, for being in the session and telling us about TensorFlow and artificial intelligence. And thank you for contributing to Devfest 2020 with GDG Cloud Islamabad.